So these are salted SHA-1 hashes. And in fact, what we're seeing here is each row having two fields separated by a tab. The first field is the salt. So remember, this is the randomly generated bytes that are created for each unique user. The second field is a SHA-1 hash of the password and salt. So this is the one that's always going to be unique, even if the same password is used, because that value on the left is a randomly generated salt. Now both of these are base 64 encoded. And in fact, what we're looking at here is salts and salted SHA-1 hashes created by Microsoft's ASP.NET membership provider that was present in Visual Studio 2010 and earlier. For many years, this was the default standard for storing passwords. And certainly it wasn't just for Microsoft. This was a generally accepted industry practice. And salted SHA-1 hashes remain one of the most common ways of storing salted hashes today. But this is weak. It's enormously weak. And I want to show you the problem. Let me now minimize this window, and behind here, we're looking at a command prompt. And the command that I've got sitting here ready to go is one that's going to run hashcat. Now hashcat is free hash cracking software. It's enormously good hash cracking software. And what it's going to do is crack our salted SHA-1 hashes. The way it's going to do it is it's going to take that file of hashes I just showed you, and it's also going to take a password dictionary. And that's the parameter you can see here, hashkiller.com.dic. And a password dictionary is just a collection of strings that are common passwords. So not necessarily actual words that you'd find in a typical language dictionary, rather passwords that are commonly used across various systems. So I now want to run this, and we're going to see how quickly it manages to crack our salted hashes. And that's it. It's done. So now that it's executed, I want to take a moment to talk through what's actually happened. First of all, what we saw scrolling through the screen was each row of our salted hash. And we can see part of the salt and the salted hash still left here on the screen. It's got some other data around it which formats it in a way that Hashcat can understand. Now off to the right, we're seeing the plain text version of that particular salted hash. So for example, Ninja, password with a 1. All of these were in the password dictionary, and Hashcat then took them, added the salts to them, hashed them, compared them to the stored salted hash, found a match, and then came back and reported that yes, indeed, this is the plain text password. Now it's the stats down the bottom that make this particularly interesting. So first of all, this only took 4 seconds to run. This was rather fast. During that 4 seconds, the GPU, so my graphical processing unit, so that's the graphics card of my PC, which is enormously efficient at calculating hashes, it managed to create 18,241.1 kilohashes per second. So in other words, it was creating 18 million hashes every second. Now because of that, it managed to recover 29 out of 30 of those stored salted hashes. So this was just a pretty short list. Often you'll find systems contain thousands or even millions of stored hashed passwords. So clearly this was an enormously effective exercise. And many people are very surprised that you can compute 18 million hashes per second. But they're even more surprised when you see just how fast you can compute hashes if you approach things a little bit differently. Let me show you the Hashcat website for a moment. Hashcat has some really interesting stats here on just how fast it can run. And in the performance section, you'll note that they talk about 4 different PCs. The top couple of rows show a couple of different GPU architectures, one being an AMD HD 7970 and the other being an NVIDIA GTX 580. These are consumer level graphics cards. They're high-end graphics cards, but we're still only talking about hundreds of dollars for something that people run to, say, play games, so fairly commonly found GPUs. Now if we scroll down a little bit, we'll see just how fast these GPUs can run for different types of hashing algorithm. So let's take that first machine, the one with the 7970. If we were using MD5 hashes, it could calculate 8.5 billion of them per second. Now that figure is so much higher than what we just saw, because rather than feeding the hashes in via a password dictionary, this example has the source passwords generated entirely in the GPU. So for example, it will simply say, give me a range of 6 to 8 lowercase characters. You don't then become I/O bound by having to feed in passwords, it can all happen internally. Now MD5 is also a much faster hashing algorithm than what we just saw with SHA-1 as well. But even SHA-1 is still over 3 billion hashes a second. So this is enormously fast. And incidentally, that 7970 launched back in 2011 as well. So things have gotten significantly faster since then. So that's all I want to cover on the hash cracking itself. Let's now look at how to do this properly. And I've got a great resource to share with you. This is the OWASP Password Storage Cheat Sheet, and it's a fantastic resource for helping you decide how to properly store passwords. Now I'll point out just one thing here, and it's this: work factor. The key thing with password hashes is that they need to be slow. So they need to be slow enough that it makes the cracking process infeasible. As the hash process gets slower, the success rate of the attacker declines dramatically. So for example, if we could make the hashing process 1,000 times slower than what we just saw, instead of 4 seconds, it's going to be 4,000 seconds, and that's only for the 29 hashes we cracked as well. Make it 10,000 times slower, and now you're starting to look at seriously detrimenting the ability to crack those hashes. A really important point here is that this protection is not about absolute security. It's not about making them uncrackable. It's about making it so infeasible that only the weakest passwords are going to be cracked, and the vast majority of them, assuming users are using good passwords, which is a different challenge altogether, are going to remain safely secured. So that's just one example of insecure cryptographic storage. Let's now move on and look at something totally different, and that's unvalidated redirects and forwards.